Well, good morning then. I think today what we will do is we will finish our discussions on the solid propellant rockets. Something amusing, I thought I should start with this. Solid propellant rockets which are known as SPR or also known as solid propellant rocket motors. Whereas when we talk of liquid propellant rockets are known as liquid propellant rocket engines. What do you think? In many textbooks you find this solid propellant rocket referred to as a motor, whereas liquid propellant rocket referred to as an engine. What do you think would be the reason for this? Any guesses or something? Let's go back and look at the construction of a solid propellant rocket. Anyway, we have a case in which we put some insulation. We will revise it again towards the end of the class. Then I have a nozzle. This is where the propellant is, maybe some radial burning grain, could be a star or something. This is your propellant. And what else did we do? We did something on an igniter to be put here. It gives a flame and it ignites it and it spreads. This is what it consists of. There is nothing else in a solid propellant rockets. If I talk in terms of a liquid propellant rocket engine, I should have tanks which carry the liquid. I have the lines, it supplies it to the chamber, and to be able to pump the, let's say the liquid fuel, I need a pump here, I should need a pump here. Therefore, I have something like a moving parts, something pump which moves, whereas and to drive the pump I need again a turbine. I have moving parts in a liquid propellant rocket, whereas a solid propellant rocket has no moving parts. It is just simple case and all that. Therefore, for some reason or the other, a solid propellant rocket, because it has no moving part, is referred to as a motor. In fact, the case is referred to as a motor case, whereas a liquid propellant rocket, considering that it has moving parts, is referred to as engine. This is the way I interpret it, but in all books invariably, in fact in your discussions when you go out and talk, people will call it as a solid propellant rocket motor, whereas a liquid propellant is always referred to as an engine. Now with this introduction, let's go back and see where we were last time. We talked in terms of the igniters required, and let me just briefly go through what we covered in igniters again. See, before igniters we were very clear how to design the burning surface area, how to be able to define the burning surface area, the configuration of the grain, the amount of thrust which is required. I can now design my grain and therefore my solid propellant rocket itself. When we came to igniter, we said I put a charge which easily burns, impinge a charge on the surface, pressurize the cavity, and then ignition takes off. But then we also told we have some types of igniters. One was a pyrotechnic igniter, in which I have a charge which is easily ignitable, whereas we also talked in terms of a pyrogen igniter, wherein we put a small rocket motor itself as the igniter. What is the principle? Let us just say whenever I make a fire, like for instance I want to light a candle, let us say I use a matchstick and light this candle. I cannot use this matchstick if I were to have, let us say, a sparkler. I do not generally use a matchstick because it requires more sustained flame, and therefore I use a candle for lighting the sparkler. Now again I say I have something like a Bengal pot. It is something like a mud pot in which I put some pyrotechnic composition. I cover it over here, it is something like this. I light it over here, and here I get the sparkler. This is known as a Bengal pot because this type of firecracker originated in India in Bengal, and therefore to light it what I use is I put a sparkler, I show the sparkler here and light this and it comes. What is it I see? A small fire to make a little bigger fire, to make yet a bigger fire, and with this bigger fire I do this, and so on. That means in practice we have to remember, to be able to ignite anything, a small fire, always you make a big fire, and so on, a still bigger fire, which is used to ignite a still bigger fire, and that is how things are. If I have a furnace, I do not put an electrostatic spark, I create a pilot flame, with the pilot flame I ignite it, and so on. And so also in solid propellant rockets, what we do is sometimes we use a small rocket motor over here, and that small rocket motor will again, let's put that down, you know, it's something which is important not only in this subject but in all other subjects. I have a nozzle here, let's say this is my case over here, I put a small rocket over here, that means I will have something like a nozzle over here, I have another igniter for it over here, and this will contain a squib and another one which it ignites, and therefore a small fire makes a bigger fire, maybe makes a still bigger fire which ignites your pyrogen, and which still makes a bigger fire which generates your thing, and therefore a pyrogen is a small rocket which ignites your main rocket. And what did we tell ourselves at that point in time? We said, well, if I have a large rocket and if I look at the pressure time trace, I have something like it takes off, it ignites here locally. What ignites? Initially it pressurizes the chamber to some small value and also transfers heat over here, and therefore I have local ignition from, let us say, 0 to 1, and then the flame spreads over the surface little bit to 2, and then when the overall flame has spread, it reaches the equilibrium pressure which we say is P equilibrium. We derived expressions, we said, you know, this can easily be predicted, and how did we predict? We say dm by dt, that is the pressure which is developed, that is the mass which is contained in this cavity, the rate of change of mass is equal to the rate at which the igniter supplies the mass at that particular time plus the contribution which comes from the burning of the propellant and the spread of the propellant minus the rate at which the float takes place through the nozzle. And we were able to say m is equal to PV by RT, and we took the simple case wherein dm by dt corresponds to the condition when the surface, entire surface of the propellant has just got ignited, that is point 2, local ignition of a small surface followed by the entire surface getting ignited, and we were able to get the equation to this curve. And what was the equation? We told ourselves, well, I write dm by dt, and you see how simple is it. M is equal to PV by RT, that is dP by dt, into volume is constant, V by RT is equal to, what is happening now, the entire surface is burning, SB into R is equal to A P to the power n into rho P, that is the rate at which mass is getting generated, minus 1 over C star into P into AT, right. And therefore when we solve this equation, we got dP by dt is equal to RT by V, and then we had this within the bracket, SB A P to the power n density of the propellant minus 1 over C star into P into AT. And what did we do? We said C star was equal to under root RT by capital gamma, which was a function of the under root small gamma into 2 over gamma plus 1. Therefore RT we were able to write in terms of gamma square into C square, and this particular equation we were able to get it in the form D non-dimensionalized. How did we get P bar? We said P bar is equal to pressure at any point in time. Let us say the pressure here is P, the equilibrium pressure is the final steady state value, P by P equilibrium is P bar, and we defined a characteristic time which came from V by AT, we brought it out, we got L star here, L star by C star we said as a unit of time, we called it as characteristic time, and we said we will take a look at it when we study combustion instability, and then we said T bar is equal to T by T characteristic, and therefore we were able to get, say, T characteristic here, TB by dt bar is equal to P to the power n minus P. Here on the right side P should be P bar, that means it must be the non-dimensional pressure. We integrated this expression and got it in the ln form, that means pressure at any point or the time between, let us say, event 2 t to event 2 starting from event 2 at any time we got it as logarithm of 1 minus p at 2 non-dimensionalized to the power 1 minus n to the power 1 minus p at any time to the power 1 minus n is the expression for that time, or rather we found it droops after some particular time. We followed the same logic to be able to find out what will be the variation of pressure, let us say P over here, T over here. We said, well, I have the ignition, the motor ignites, it keeps on burning, and then all the propellant gets burnt. What will be the signature what I get over here? What will be the equation to this? How will it behave? Does it go like this, or does it go like this, or the shape we were interested? And the equation we got for this was very similar. Well, all the propellant is getting consumed over here, therefore the equation for that particular one which we derived in the last class was dp by dt again RT by V into the rate of depletion is minus P into AT by C star, which is m dot n, correct, and therefore we did the same non-dimensional RT is equal to gamma square into C star square, and therefore we got gamma square C, gamma square into C star squared divided by V. We took AT outside and we got the value of C star again coming over here as P, and therefore this negative sign comes over here, and therefore now this becomes your L star, that is volume by throat area, that is characteristic length, and now I have C star over here, this is unit of velocity, this becomes L star over here, and therefore I could also write this particular equation in the form maybe 1 over L star divided by C star, which is equal to your characteristic time, that is 1 over characteristic time, because length over velocity has a unit of time, and therefore P over here we got this as equal to dP by dt. And then if I were to divide both the pressure here and pressure here by equilibrium pressure, I can write it as dP bar, and here I take this over here, I get dt bar, that is non-dimensional time and non-dimensional pressure, is equal to P bar, or rather this equation, mind you, there is a minus sign over here, there is a minus sign over here, and this tells me that dt is equal to dP by P minus, or rather the time taken for it, let us say this is the time at which burning gets completed, TB, burning gets completed over here, therefore I get T bar minus TB is equal to logarithm of the, now I have to switch the value, that means my final pressure will come at the bottom, and therefore minus will come over here, that is ln of, let us write it out, minus ln of the final value minus ln of the value corresponding to the, at any time I have the value of P bar, that is I am non-dimensionalizing it, I am writing this value, the value corresponding to PB gives me the value of PB bar over here, and therefore I get the expression as T bar minus, this should have been T bar B is equal to ln of, this becomes negative, therefore PB by the value of P over here. In other words, the decay is exponential, and to reach 0 value it is going to take a very long time. And I did it dimensionally the other day, and what did we do dimensionally? We could have directly integrated this value over here, and if we had taken this, I would have got gamma square C star by L star, or rather let us do that, we must be able to do this in different ways. We could have got dP by dt is equal to gamma square C star by L star into P with a negative sign over here, gamma square C star V by AT is L star over here, and if I were to integrate I get ln P is equal to minus gamma square C star by L star into T minus, that means here I should get P divided by the value, or P minus ln Pb. This if I were to write without the limit I get T, or rather I get P by Pb, that means ln P minus ln Pb is equal to e to the power minus gamma square C star by L star into T minus Tb. That means the pressure continually decays with time. Therefore, why am I doing all this, and why are we doing all this? See, there must be some reason, right? The reason is, now what is it we have established? We say whenever a rocket motor ignites, the pressure changes with time, starts slowly, builds up flame spread, goes over here, then reaches, if it is neutral it goes like this, if it is progressive it goes like this, if it is regressive it goes like this. Mind you, this particular zone is equilibrium pressure, right? That means a steady state pressure. At the end of this, what happens is, well, all the propellant gets consumed, it goes like this and comes back over here. This is the transient for ignition, ignition transient. This is the period of steady burning, which will be much longer, and this is the time when it burns out, or you have, we called it as tail off, right? Now, how do I use this? You know, I fire a motor, I get these signatures. How do I find the time of burning? I find the curve goes like this, steadies out, and it comes like this. How do I find the time of burning? It becomes a little complicated, and for that there are standard procedures how we do it. I plot, let us say I consider the case of neutral burning, one case. What I do is I plot a tangent to this particular graph over here, I plot a tangent to this curve over here, I get a particular point over here. Similarly, over here I plot a tangent here, I plot a tangent here, I get a curve point here. I say this is point A, this is point B. And now see, here also some burning is taking place, here also some element, you know, I say the burnout is not sharp at this point, it would have been somewhere here. This particular distance from A to B is called the burn time. And it is denoted by the word Tb. See what is happening? See, burning has happened somewhere here, even though I say some little bit of propellant is still burning here, it is there. Therefore, this particular distance or the time period between A to B is what we call as a burn time. And this is how we characterize a solid propellant rocket motor. That means we say that the burn time of this motor is so many seconds or so many minutes or so. But then we must also realize during this period, when before the burn time, it is still giving you some momentum, it is still giving you some impulse, and here also you get some impulse. Therefore, when I want to define a mission, and mission is to get impulse with which the payload goes up, this also contributes and this also contributes. In other words, I take the maximum pressure reached over here, I find the value of pressure over here at this particular point as, let us say, the value corresponding to A divided by, let us say, 1/10, that is 10% of the value here. Similarly, I get the value of Pb here, I get 1/10 of the value here, that means the pressure corresponding to this point is equal to pressure at this point is equal to pressure corresponding to B divided by 10. And now here also I get a certain impulse, here the impulse is going to be very small, and this particular time between this to this is what we call as the time of action of the motor, or action time. Denoted by TA. In other words, when I have to plan a mission, like we want to launch a missile, let us say, I get something over here, I need this particular time. Whereas to characterize the motor per se in a test or something, well, I am interested in the burn time, and always we see, well, the action time is greater than the burn time. Well, this is all about solid propellant rockets. Now let us go back and examine one or two small problems we can have in solid propellant rockets. You know, why I am considering this is, whenever we make a rocket, let's say I make a sketch of a motor, let's say it's radial burning, I put an igniter, and we told ourselves the other day most of the igniters are pyrogen igniters, because normally the rocket motors are quite substantial, that is, the solid propellant rocket motors are quite large. For I have the propellant here. Now I make an igniter, and how do we design an igniter? We were very clear, it must pressurize this cavity to some value, not very high value, such that a flame can be near the surface, and also give some energy, and we said propellant requires some minimum energy for ignition. I get some plumes and it ignites a particular surface. This is all the requirement, and thereafter the flame spread and pressurization takes place, and we had this particular curve, local ignition, flame spread and the pressurization. But very often when we do these tests, what we find is, instead of the pressure going like this, very often the pressure goes like this and comes down like this. In other words, I get a peak pressure. That means I get something like an ignition peak. In the process of ignition transient, I get something like a peak in the ignition, and this is detrimental, because all of a sudden I get some thrust which is not desirable. Why should such an event take place? Let us take a look and what are the parameters. When we make this propellant, how do we make a propellant? Well, I take a case, motor case like this, a solid propellant rocket case. Inside it I put a mandrel. If I want to make a cylindrical grain, I put a cylindrical rod over here, pour the propellant over here. If I want to make a star grain, well, the shape of this mandrel which I use should be a star shape, and then I cure it, and then I remove this mandrel, therefore I have this particular shape of the grain over here. And on removing, sometimes to remove the grain is difficult, and therefore we use some agents which are like silicone oil or something, which are essentially insulators, to be able to easily remove it, and I form the grain in this particular way. Now if the surface of the grain is such that it is not easily ignitable, what happens? You are transferring energy, the grain gets heated, and as it continues to get heated, when it begins to burn, it starts burning at a higher temperature, and since it starts burning at a higher temperature, the value of R is now influenced by the temperature sensitivity factor, and therefore since this you have a burning takes place at a high temperature, it produces much more mass, or it burns with a higher speed, and therefore you have a higher amount of mass energy which is getting released, and therefore the pressure could go up. This is one reason. The second reason could be, maybe I have velocities and it could lead to higher burning rates towards the end, and that is also possible. But to be able to prevent this, what is normally done is, we take something like an emery paper and remove the surface defects and ensure that the surface of the propellant is easily ignitable. Let us put it down. To prevent ignition spike, ignition pressure spike, what we do is, maybe we emery a surface. Take an emery paper, maybe make the surface, make sure oxidizer and fuel are readily available and it catches fire easily. If not, maybe you have to make sure that the surface is such that some other reason like erosive burning, which I will consider shortly, does not lead to an anomaly and have a pressure spike. Instead of the motor burning like this, it must not happen I have a huge pressure spike. I can always tolerate something which is small, but this must not happen in practice. This is something we have to guard against. Something which I missed out telling when we talked of igniters was, very often when we ignite a motor, the gases are going out and some of these motors have to ignite in vacuum, and therefore we put something like a closure here. We initially close the thing like this, and when pressure builds up this goes off, and once the motor is ignited this gets thrown out, and let us make sure that this is around 5 bar to 6 bar such that some minimal pressure gets created. This is known as a nozzle closure. Well, these are all about solid propellant rockets. We have considered the burn rates, we have considered how to go about making a grain of a particular configuration to get a particular thrust, and then we looked at igniter, we looked at the action time, the burn time, and therefore maybe we should put things together at this point in time before we close our discussions on the solid propellant rocket. Let us see what we could think of. We talked in terms of burn rate R. How did we define the burn rate, or how did we determine the burn rate? Well, we said I can make a propellant, a small strand, maybe something like maybe a diameter, let us say 1 centimeter or so. I could put it in a chamber, I pressurize the chamber to whatever pressure I am interested in, then I ignite the surface, maybe I measure the burn rate when it propagates through a particular distance, I control the pressure in this chamber, and this particular chamber in which such strands are burned is known as a Crawford bomb. It is something like a bomb type of a calorimeter in which I burn the propellant, but all what I do is I put a fuse wire here, I put a fuse wire here, I give a timer, the timer tells me it starts over here, stops over here, this length is L, L divided by the time is the burn rate R when the chamber is pressurized to some level. Now I use this burn rate in a rocket motor, and well, the rocket motor, let us say the same end configuration is like this, and in the rocket motor what I have, maybe the diameter is D, the throat diameter is dt. I want to find out the burn rate. I measure over here, it gives me let us say 4 millimeters per second at a pressure of let us say 5, or let us say standard pressure 7 MPa. Here the chamber pressure is 7 MPa. The question is, will I get the same value of R or should I get a different value? What is your take on this? How would you feel? Should it be the same? I measure in a strand, I take it over here, I put a same pressure ambient, I measure a burn rate of 4 millimeters per second at the same pressure as is over here, and I want to measure the burn rate in the motor, because I use this to be able to design this. Will it be the same or should it be different? If it is different, why should it be different? Any guess on this? How would you look at this problem? To be able to answer this, we again go back and write what is the equation we derived for burn rate. We got the equation R is equal to APN. How did we get this equation? We said, well, I have the surface, the flame is standing off at a distance x bar from the surface. Please keep our discussions very clear. And how did we get this? We said R is equal to the heat which is given over here, thermal conductivity of the gas above the surface, into the temperature of the flame minus temperature at the surface divided by x star is the heat which is conducted, divided by rho p into specific heat into surface temperature minus the initial temperature plus the exothermity at the surface. We derived this based on the simple model over here. Now can we look at this for the experiment over here and the experiment over here and say, would it be different in the two cases or should it be the same? This is a perennial problem we have with solid propellant rockets. Now what is happening? Here the ambient is all cold gas, even though it is at the same pressure. Here the ambient is hot gas, therefore I will have heat radiation coming on the surface. In other words, when I test a motor, I will have something like Q radiation coming on the propellant surface. I could also have in a radial burning grain Q due to convection coming on the surface, and therefore the burn rate in a motor should be higher than in when it is tested over here, and therefore to determine the burn rate what is done is you have to test it in a small solid propellant rocket, and these rockets are what are known as control blocks or control round, because I cannot really use this standard apparatus to determine the burn rate. I have to use this because it is more representative. And what do I do with this? Maybe when I am developing a propellant, different formulations I try, I fix the formulation here, but the final burn rate is always derived with a small solid propellant rocket itself, which is known as a control round. In India we call control round as Agni rounds, but mind you the name should be control round. Let us not confuse it with Agni missile, maybe we will talk about it later. Small rockets may be diameter around 200 mm, length around 400 mm block, cylindrical burning is what we call as a, and that is how we determine. And how do we determine burn rate? Burn rate is equal to web thickness divided by the web burn time, and that is how we do, we go ahead and do it. But now the problem is still worse. I come to this case of, let us say I consider two cases. Well, we said the solid propellant rocket of Space Shuttle is a very large motor, diameter is around 3.8 meters diameter, the length is around 40 meters, this is one motor. Let us say it is also, let us say some star shape, but we just say a simple radial burning outside. Let us say I have another motor using, here we said P-band propellant, the same P-band propellant in a small motor, not a control round, but say let us say in a motor, let us say 10 meters long, maybe diameter of 1 meter, similar grain. Will the burn rate in this and this at the same pressure be the same or different? Again I look at the radiation depends on the mean beam length, therefore I expect the burn rate in a larger motor to be different, but it is not necessarily true. There are other factors like mechanical properties of the propellant. Why I say mechanical properties? Mechanical properties could be hardness, could be tensile strength, could be the ductility of the propellant, and during burning I could have some deformation taking place. All those things is going to affect my thickness over here, and therefore scaling of burning rate with size of the motor or size of the rocket is always of interest, and we should have some say. But I observe that when you have some medium sized motor and you go to larger size, the increase in burn rate is something like 4 to 6% generally, and after a particular size it does not really affect it significantly, but we have to verify it through models. And what are the models we use? Again we go back to our basics, write the equation, find out what is the role of convection and radiation, and solve the problem. It is simple. This brings me to the last point, namely if we were to have something like a long propellant grain, like let us say I have a internal burning grain, let us say radial, the initial cavity diameter, which is also defined as port of a rocket motor, that is the cavity, that is the port cavity, is of small diameter and it burns at the surface. Let us say this is the propellant grain, gas is coming out. Let us plot the value of velocity of the gases which is moving here, mean velocity of the gases as a function of length, starting from the head end towards the nozzle end. Here there is hardly any velocity, but more and more gases are flowing, therefore the velocity is increasing over here. Velocity is maximum at the nozzle end. Now what does velocity do to a surface which is burning? Well, it can erode the surface, like in a river. Let us say a river is flowing, and what does current of velocity do? It drags the sand from the river, So also I could have something like erosion, let us write it down. It could erode the propellant surface. In other words, I could have something like an erosive burning. Mind you, propellant was heterogeneous composite, it is sort of eroding the surface or erosive burning, but more than erosive burning, I find velocity here is higher, therefore my Nusselt's number or my Reynolds number at the point, let's put it down, let's now write it. I have Reynolds number as a function of length. Well, my Reynolds number is increasing. If my Reynolds number is increasing, well, my Nusselt's number or heat transfer is going to go up. Therefore, I am also going to get increased convective heat transfer. In other words, I can talk in terms of erosive burning arising from convective heat transfer, and when we do such a modeling, again it is simple. You calculate the new value of heat of convection is equal to function of Reynolds number into Prandtl number, and this we write in terms of Nusselt's number. Nusselt's number is equal to hd by k, and therefore I can always find out the Nusselt's number. Once I know heat transfer, I can find out what is the Q convection is equal to h into delta T, and therefore I can find out the increase in rate, and when I do that I find the burning rate can be put in terms of a constant into something like a Mach number into the pressure to the power C. The value of the exponent C is typically between 0.7 and 0.8, which is something like saying, if you look at the standard correlations for Nusselt's number, you get Nusselt's number in a turbulent flow is equal to 0.023 into Reynolds number 0.8, Prandtl number to the power 1 by 3. That means it does show that convection plays a role. In addition to pressure, I have Mach number effects, and this is what gives me the erosion effect. And this erosion effect, because it increases the burn rate, can also lead to, instead of the ignition going like this, at this time the port volume is small, I could have an ignition spike, that is pressure versus time, I have an ignition spike over here. Well, we can keep on talking of these different things which alter the basics with which we studied. Something which I thought I should bring out was, we told ourselves, you will remember, that the solid propellant rockets could be either extremely small, extremely large. Supposing, let us say I am launching a particular solid propellant rocket, it has a nozzle, and to be able to stabilize it, sometimes the thing is spun, it rotates, or rather I have, let us say, an end burning grain, something like this, it is burning over here, it is being launched like this. This is a case wherein I am spinning a radial burning grain over here. And why do you spin? To make it stable, like just like we have a top which spins, which is more stable, I sort of spin this motor, or this is just linearly accelerating. Now what is happening is the burning surface is over here. Therefore, in the frame of reference of this rotation, I have aluminium and all which is burning over here, it gets pushed towards the surface, therefore I get the effect of local acceleration, and the effect of acceleration is to be able to either push it away or push it towards the surface, and therefore I can say, well, acceleration will affect my x star is the flame standoff, and therefore it will also affect my burn rate. And you can have a simple model. How do I find the effect of acceleration? All I have to find out is how does the acceleration affect my standoff distance from this. If I can find it out through a simple model, well, I can do it. And what we do, I know the mass here, I know the centrifugal force here, I know the acceleration over here, I know the mass of aluminum particles which are burning, and therefore I can do this problem. And this is how maybe research continues in the area of solid propellant rockets. Well, this is all what I thought I should say, but let's quickly revise through and then address one or two of the very major issues which were faced in solid propellant rockets, namely the control of thrust. I think I'll do that. For that I come back over here Just let us quickly revise in 2 or 3 slides what we have been talking of. This is an igniter, maybe a pyrotechnic igniter. It produces these plumes, impinges on the surface, ignites the surface, also pressurizes this cavity. That means these are the individual plumes which are igniting the surface here. The flame spreads and then the gases move out through the nozzle, and this is how ignition takes place. Let us go to the next one. This is a pyrogen, a small solid propellant rocket. This has a pyrotechnic igniter here, squib over here, burns here, then it burns here, ignites this surface and flame moves forward. That means a pyrogen igniter is a small solid propellant rocket. It has a regular propellant. We will take a look at one of the propellants for this, and this is the main propellant which it ignites. See, this is how a pyrogen propellant grain looks. Well, see, it is just something like a solid propellant rocket, only you do not need so much of propellant. Therefore, I find I give a multi-point star. The red is what is the propellant. I have all these things. I ignite the surface, this generates hot gases, and that is what ignites my main motor. We said gases must be, hot gases must be contained within this port volume or cavity. I use a nozzle closure. The moment pressure builds up, well, this is sent out, and therefore flow through the nozzle gets started. Till then I sort of make sure that the ignition takes place in a chamber which is sort of enclosed on all sides. This is known as a nozzle closure. It is just something like a small surface which is some ablative surface which is bonded over here by glue, and the moment it develops some thrust, it is pushed out. We use some such nozzle closures in liquid propellant rocket engines also. We will cover it at that point in time. We talked in terms of burn time, 2 tangents. This is shown for a progressive case. A tangent here, A to B, is what is the burn time, and maybe 1/10 of the pressure, 1/10 of this pressure over here is what is the action time. Well, these are all about solid propellant rockets. Now, having done all this, let us put everything together in a single diagram. What are the components of a solid propellant rocket? Well, propellant, basic. It is contained in an insulation or a liner. Then after this insulation I have another liner. Make sure that it is compatible with this insulation such that heat does not, when motor burns, the heat does not sort of allow the motor case or the case which is a metal to burn off. Therefore I have a propellant, I have a case, I have insulation, and liner is also a form of insulation. And then I have this as a nozzle. The nozzle could be sunk into the propellant, and it could be made to flex. We have seen that when we talked of in terms of nozzles. We have a nozzle closure over here. I have an igniter which could be a pyrogen igniter or a pyrotechnic igniter. Well, this is all what a solid propellant rocket is, and we said it called a motor because there are no moving parts in a solid propellant rocket. Having done all this, I thought let us review 2 practical problems which have been encountered during the history of development of different rockets, and I just choose 2 of them because all of us have heard about it, and let us clarify what really happened. One is, we talk in terms of solid rocket boosters for space shuttle. Our interest in this is, we told us the solid rocket boosters for the space shuttle in USA was by far is the world's largest solid propellant rocket. It uses PBAN, polybutylene acrylic acid acrylonitrile as a propellant. This is the fuel binder. Of course, it contains AP, large amount of aluminum as in all solid propellant rockets. And what was the problem? In one of the shuttle launches, this happened in 1986, I think January month, maybe 28th or so. There was one particular flight known as the Challenger in which it misbehaved, and the entire crew, 7 crew got burnt out, they all died. And also not only the crew, it was the first time that they took a civilian into space. They took a school teacher, right? What was the problem? Let us try to understand, because we have studied quite a bit and we must be able to understand what really went wrong. Well, this shows the space shuttle. What does the space shuttle consist of? it consists of a central engine which is a hydrogen oxygen cryogenic engine. There are 3 of them here, they burn simultaneously, and behind the driving for these, this is the space plane, and behind the space plane you have a huge liquid hydrogen tank, and at the bottom of it you have the liquid oxygen tank. This is the huge liquid hydrogen tank. You need a huge tank because liquid hydrogen is not very dense. You have 2 solid rocket boosters, and first what is done is these 3 liquid engines fire. They make sure that adequate thrust is developed, because you can always switch on and switch off a liquid propellant rocket, and once it has developed the particular thrust, the 2 solid rocket boosters are fired. Mind you, this is what we said is around 3.8 meters diameter and around 40 meters in height, and this begins to fire. And in this particular launch, it happened on a cold day. The temperature at the ambient was around -1 degree. Previous night, it was in the morning around 8 o'clock or so. The previous night the temperatures went down as low as -15 degrees centigrade, and this shows it was a perfect launch, it takes off beautifully. But then after some time, let us come back to the earlier slide. After some time, maybe around 0.6 seconds after ignition of the solid rocket booster, around this region on the right side engine, little bit of gas was found to escape. Let us see the problem. Whenever we have these huge boosters, what happens? How do we make the construction? It is very difficult to have a entire motor or entire grain to be cast together. We make it into blocks and then assemble them together. Each block is known as a segment, and now therefore you make small segments. The solid propellant segments in the case of space shuttle consists of something like I think 6 segments, and what is done at the factory wherein these things are made itself, some of them are done, but 3 of the 6 segments are assembled in the factory such that it is still transportable, and then in the launch site maybe the others are assembled together. How do you assemble it? You have the case over here, you have the case over here. You need to make sure that these 2 are put together or joined together such that no leakage is possible between this. In other words, one segment, maybe I will put something over here, insulation, then I have to put the other segment over here. This has to be joined together, maybe I should be able to join it in some form over here. And how is it joined? We put O-rings. In other words, let us try to make a sketch of how the O-rings function. See, how do you assemble an O-ring in any problem? I have a O-ring groove, I put the O-ring over here, and when I have to assemble this, the O-ring being flexible, it makes this junction to be airtight or leak tight, and therefore 2 O-rings are used, and these O-rings are of rubber. The rubber O-rings which were meant for this have not been tested for temperatures less than 15 degrees centigrade. The previous night was cold, this particular launch was on hold for some time, and therefore what happened? The O-ring which is resilient at ambient temperature becomes rigid and hard, and when it becomes hard, it allows the gas to flow by, and therefore at the segment joint what is available, some little bit of gas begins to flow back, and the moment it is ignited within 0.6 seconds, people saw, or when failure analysis was done, they found some gases were beginning to escape. These gases are escaping, but our propellant is highly aluminum. Therefore what does aluminum oxide do? It goes and blocks it. Well, the motor is still safe, it keeps on going further and further. From 0.6 seconds at which the O-rings have failed, up to something like 60 seconds, 62 seconds, well, the flight was perfect. It keeps on going because aluminum oxide, there is a hole, aluminum oxide blocks it, the chamber continues to function well. But when we fire a missile or a rocket, it goes through the atmosphere at around maybe something like 13 kilometers height. When it was going, we have wind in a particular direction, and the bottom wind is in the opposite direction, we call this as a wind shear. Some wind moves in this direction, some wind moves in this direction. When the vehicle is moving up, let's again put it together. Now the vehicle is moving up, and what is happening? Some wind is in this direction, some wind is, it sees wind shear, it gets shaken, and therefore at that point in time the breach takes place. At the bottom on the right hand side, the opening opens out, some flame comes out, and when this flame comes out, it hits against one of the attachment which is attaching this to the main rocket, and that gives way, and this fellow comes out and it gives a thrust in some other direction. Not only that, this flame hits against that what we said is a hydrogen tank which is available in between, spills the hydrogen. This happens at a height of around 14 kilometers, and well, what could happen? Well, there is a huge fireball and the entire mission is a failure. Therefore, we do see the corrective action of aluminum oxide in sealing the hole. In fact, one of the recommendation is whenever you use an igniter for pyrogen, we never put aluminum because the nozzle will get clogged. But here it helped, but the failure was because of the O-rings which were not doing the job well. Well, this is about space shuttle. One last example I will take, this is also something which is interesting. I will cover the details of this when I look at instability. We have the second largest motor, I just picked on these two, something like space shuttle has 500 tons of propellant. The second biggest is something uses 280 tons of propellant. This is in the case of Aerospace. Aerospace is a French rocket, and it uses something like a HTPB based propellant, hydroxy terminated polybutadiene. And in this particular case what happened is, again being a large rocket, we have segments, different segments, and how do you assemble the segments? Well, in between the segments I put glue or some inhibitor, join it together, and let us now consider a segment joint. The segment joint is, well, I keep this open, I have one segment over here, this is my inner diameter, I put a segment joint over here, then I have the next segment coming over here, and then I have the inhibitor over here. Now when the propellant burns fast, whereas this fellow does not burn fast. Therefore after some time I have the inhibitors standing like this, the propellant is over here, the flow takes place here, and therefore some eddies are formed. These eddies in the flow have a characteristic frequency or disturbances, and these disturbances get amplified, and the thrust, instead of being something like this, starts oscillating, and the oscillation is because of the eddies formed, because this fellow projects when the propellant has burnt over here. Well, I have this protrusion here, I have something like this standing, and this causes the pressure to oscillate. We will see such mechanisms when we look at the chapter when we look at combustion instability. Well, this is all about solid propellant rockets. Maybe we all should try different problems, and maybe one problem which I think you all should think of is, maybe if I am given something like a thrust of a solid propellant rocket, given the specific impulse of the rocket, I can find out what is the mass flow rate. I can also use the C star, find out what is the value of AT or what is the value of P, and using P and the burn rate relation R is equal to APN, find out the burn rate and then solve the problem. This is how, it is quite simple, and in the assignments I have given you something like 10 problems, maybe you all should try it out. Well, we have finished the portion on solid propellant rockets. In the next class I will start with liquid propellant rockets. Well, thank you then.